than R, that's for sure.
We need to record some of this and send it to Adam.
No, we're not recording yet, right? We don't.
Even
we
like
don't
the
want to start World War
Adam
III.
is given for Glemnet and Caret package, where you just put a grid and then you run this thing, and in the bootstrap matrix you can collect all your mean square errors and run the.
Yeah, no, that's good.
That's also very cool.
That's
it's
good.
like
yeah, it is. It is. I mean, it's a lot of Python has learned from R, like pandas and stuff. That's all.
Yeah. In fact, it was
you can run R from Python actually, so it's not so strange. So you can I mean, there are ways you can incorporate R code into Python code. So.
Yeah.
So it's all the same. I mean. But,
okay, I think we can get started.
All right. Okay. Yeah. So I thought I would go briefly go back over the SVM because I also got some colored markers I wrote on my board here, so maybe it looks a little bit clearer now. So let me go to the board here and let me try to move the camera over so the board can be seen. You see how's this? Can you see the board?
Yeah, I
very clearly.
Yeah.
Okay. Okay, so this is the picture that I drew, except I have better colors now. So the idea again is to find this line in 2 dimensions. It's a line, but in general it'll be some hyperplane that best separates the 2 sets of points, in the sense that the margin we can put around the line is the widest possible. So what we have is our line here, and we can look at those points for which are closest to this line. And so there will be these 4 points here. And we want to find this line that maximizes this distance to the closest points, because that'll be the one that has the widest margin around it. And so the way we're going to try to figure that out is to parameterize the, in this case, line, in general, a hyperplane. And in general, we can write such a hyperplane as an equation, some vector beta, is a set of points such that beta of x is equal to some constant c. So it's a set of all points beta such that when a set of all points x such that when you dot it with beta, then it's equal to a constant c. And it turns out then that beta is a vector that's perpendicular to the plane. So here's our hyperplane H, and beta is here, and that turns out is perpendicular to H. So we have a beta here perpendicular to the line. We have this little vector R here, which is also perpendicular to the line. And so if you have 2 vectors that are perpendicular to the same line, or in general to the same hyperplane, well, then they must be parallel. So that means that this little vector here is a multiple of this vector here. So we can write here that this vector R here is the sum alpha times the vector beta.
Hey, sorry, Niels, one question here.
Yeah.
How are we ensuring that beta is perpendicular to the hyperplane unless we are doing a dot product and saying it's equal to 0? Probably
No, because that's yeah, but it's only when it goes. It's not. It's you see a vector here on the. So let's say we take a vector here on the hyperplane, right? That'll be this vector here.
Yeah.
Yeah, that's not perpendicular to beta.
Okay.
So it's when you if you were to move this hyperplane through the origin, then beta is perpendicular to it. If you move this, if this is a real hyperplane, a linear hyperplane, then that goes through 0 to the origin. Then it is perpendicular to but it's not perpendicular to vectors here that are on the line. In fact, they all have the same. The dot product all have the same value. You have to be careful that the points on the line, or they're described by vectors that start at the origin, right? So a vector. So a point on the line here that corresponds to this vector here. And that's not perpendicular to beta. So our little r here is a multiple of beta, because these two, this vector here and this vector here, they are parallel in the sense because they are both perpendicular to the same line. So let's try to write this r here as a vector x. So that's a vector that goes from here up to the point, and then the corresponding point on the line, that's what we call A here. So then what we have is that r is x minus A. We have here A, and we have here x, and here's our little r here in between. So r is equal to x minus A. So what can we say then? Well, we can look at alpha. So r was alpha times beta. Alpha times beta is then equal to x minus A. So now dot this equation here with beta. So take the scale up the dot product of this equation here with beta. Well, I get alpha times beta dot product with itself. That's the norm squared. Beta is equal to beta dot x minus beta dot A. But now A is on the line. So A is one of the points here. That means that beta dot A is equal to C. So this is equal to beta dot x minus beta dot A is C. And so again, I get an equation for alpha here, namely alpha is equal to beta dot x minus C divided by beta norm squared. So again, x is one of these points here that are closest to the line. So this is what we call the support vector. So x here is a support vector. Here another support vector would be here. And here would be another support vector. What we get is that this alpha here is can be written in this form. And so the norm of r, which is the norm of alpha times beta, so that'll be the absolute value of alpha times the norm of beta. And that'll be the length of this here. Let's call this mu. So this is the distance from the line of these points that are closest to the line. They all have distance mu given by this formula here. I can plug this into my expression here, and I get the formula that mu is equal to alpha beta, and this was equal to, well, absolute value of alpha is equal to the absolute value of this divided by beta squared. So when I multiply by beta, I cancel one of the two things, so I get that this is equal to the absolute value of beta dot x minus c divided by beta. And then then we start doing this stuff by saying, well, if we scale beta here, so if we take another beta here, which is just a multiple of beta, so we can scale beta here by going up or down, as long as we're just multiplying by a scalar, we'll get a vector that's parallel. And so what happens if we take another vector?
Sorry to interrupt.
Yeah.
This might be a stupid comment, but still, you have written beta dot x equal to c, right?
Yeah.
So why beta dot x minus c is not 0? Why mu is not becoming 0 there at the top when we assign it?
Yeah, that's because this is not the same. So yeah, I'm using.
Or we use, this is a different constant.
I'm using a notation I shouldn't. So let's say that the H is the set of all U such that beta dot U is equal to C. So set of all vectors. So here is a vector U. This vector here will be one of those vectors. X is in my equation here. X is the one of these support ones here.
Correct, vector to point A.
Yeah, I was just using the
Okay, yeah, sorry.
wrong notation.
Yeah.
So if I scale beta by some lambda, so instead of looking at beta, look at lambda times beta. And what happens to the equation here? Well, I just multiply the equation by lambda here, and so the equation here just becomes W dot U is equal to lambda times C. So all that happens is that when I scale my beta here, I take a multiple of beta, all that happens is I change the constant here. So if I scale correctly and take a W such that this thing here becomes 1, right? If I take W here, I get alpha times W divided by lambda is so that's equal to, well, let me not do this. Can you still see it?
Yep. Yes.
So if I use this here, I get lambda W. No, sorry. If I multiply this whole thing here by lambda, I get lambda times mu is equal to lambda beta dot x minus lambda b divided by lambda w. So if I choose the, so I can write this as lambda times mu lambda w is equal to w dot x minus lambda c. This lambda c I'll call c prime. And so if I choose the correct lambda here, I can make this equal to 1. I can choose any, this should be a beta. So I can just choose a lambda such that this side here is equal to 1. And so if I do that, I get the equation that 1 is equal to w dot x minus c prime. And so I can write and so what I get here is that w norm w dot mu is equal to 1. That's what I get out of this. So what you can see is that if I want to make mu here as large as possible, that means I want to make this as small as possible. So I want to find a w that satisfies this condition here for all the points, all the support points, all the points that are closer to it, and such that this, the norm of it is as small as possible. Once I get this, I will get that mu is the largest possible. So the condition I get for all the other points here, so I have a data point here, say xi here, so that's another data point. What you get is that for those data points, you have that w dot xi minus c prime is bigger than or equal to 1. And so again, by choosing the direction of beta here, or choosing the direction of w, the right way such that it points in the plus direction. So if these are the ones that have labeled +1, these are the points that have labeled -1. And if the label for xi is yi, so y is ±1, I can achieve that that this by multiplying by yi, I get that this is positive. So I can write this as yi times w dot xi minus c prime is bigger than or equal to 1. So this is just if so this absolute value here is bigger than or equal to 1. Well, this can be, the stuff that's inside can be positive or negative. And if I arrange it such that when it's negative, well, then yi is -1, so I get negative times -1, well, that's positive. And vice versa, if it is positive, then yi is +1. So my problem here the solution, at least the, what can I say, not the solution, but the mathematical problem that we end up with for this geometric problem is to find w such that w dot xi minus c prime times yi bigger than or equal to 1 for all data points xi, and such that the norm of w is minimal. So this is a convex optimization problem. It's finding the minimum value of w subject to these constraints here. And there are ways to solve this, which we won't go into, but one can formulate this in terms of what's called the dual problem. So the solution here is the same as find numbers alpha 0, alpha 1, up to alpha n minus 1, so their number of data points. Capital N. So the dual problem is to find numbers alpha 0 to alpha n minus 1 that maximizes the sum of the alpha I minus, or is it, I can't remember, it's minus or plus.
And you cannot see the whiteboard because it's coming in front of you. So sorry.
What's that? Is it plus?
No, we cannot see the whiteboards. Okay, now better. Yeah.
Okay. So it's yi, yj, alpha I, alpha j, xi dot xj. So this is I equals 0 to n minus 1. This is I and j. This is double sum such that this is, find these numbers that maximizes this expression. And such that the sum yi alpha I is 0, and the alpha i's are all bigger than or equal to 0. So this is the dual problem to this optimization problem here. And if we can solve this, so if we can find these things, in which you can do in many different ways, like taking partial derivatives, put them equal to 0, or some stuff like that. Then W, the vector we're looking for over here, simply becomes equal to the sum of alpha I times xi. This just becomes this linear combination of the support vectors, and the alpha I is 0 if xi is not the support vector. So for all the data points that are further away than mu, so whose distance is bigger than mu here, the corresponding coefficient alpha I will be 0. So that's the that is the formulation of the optimization problem that we will use to be able to solve in order to find this this line. And there are ways to do this. I won't go into it, but there are different ways of doing this. It's like a quadratic optimizer can do this, but there are other algorithms that can do this. But we won't go into the actual way of solving this, because that's a lot of math that goes into that. But let's take it from there and expand on the model here. So let me plug in.
Actually, can you talk a little bit about the solution to this problem? Is, you know, it's like the gradient descent has some fine tuning in terms of the learning rate and some slowdown as it approaches the minimum. Do those kind of problems, I can't quite see the optimization here, but is it a better optimization than a kind of gradient descent type convergence? Does it converge faster to the solution? Because
no, I mean you don't really So since it's a constrained optimization, you can't just use gradient descent here because you have to satisfy these constraints. So what you can do is that there are different number of different algorithms that allow you to do that. But so you can't just so if you start using gradient descent, then you're gonna change one yi at a time. But
I wasn't suggesting using gradient descent. I was wondering if the convergence of these algorithms are better than a gradient descent. I'm not comparing it to the same problem. I'm saying, we have certain problems to worry about there, so in other words, is the determination of the hyperplane a better solved or a better understood optimization problem than, say, the ones we looked at with logistic regression?
Well, I mean, it's not a. I mean, the algorithms are different. But one thing you're trying to maximize something which is well, it's the same problem, but. I mean, you probably could use. I mean, the thing is that you have when we're doing gradient descent, you're just trying to find a point where the gradient is zero.
Right.
But that's not enough here, right? Because you still have the constraints involved. So you can't just find a set of alphas
right.
such that the gradient is zero. They won't satisfy the constraints. So it's a constrained optimization problem, which requires different methods to solve. Let me put my headphones.
And also here we still have the problems of high dimensions, right? For example, because you're still searching for a hyperplane in whatever n your feature space is, right?
Yeah, I mean it's a quadratic. So you have quadratic optimizers that can solve this, but if you have too many, so the problem is how it scales with the
number of feature vectors.
Yeah, with the number of data points. Yeah. So if you have very large data sets, you're going to have a lot of alphas.
But you were actually able to cut off the alphas that lay outside the region of U, right?
No, that was beta.
No, I mean the truth is, yeah, that you only get those. The only non-zero alphas are those that correspond to the support vector. So those that correspond to the vectors that are closest to the
right. So I could have a large number of data points.
What's that?
I could have a large number of data points that lie outside, and they don't.
Yeah, sure, that's right. But I mean, you have to find them, right? You still have to find the ones that. You have to find the ones that. I mean, you have to find the hyperplane that.
Yes.
That does it. So it's not so clear how it works. So you still have to look at this optimization problem with an awful lot of variables. So we have very large data sets. So capital N is very large. You have a lot of variables. So the fact that you show that at some point of time when you compute it, you get a lot of them are zero. It's not really helping you so much because you have to find them. So it's a fairly complicated problem to solve directly. I mean, there are algorithms that are some pretty clever algorithms that can solve it. But again, if n is very large, it's very slow, and so it's hard to solve it for very large data sets. So the computationally it becomes very difficult. But let me go to the other stuff that I wanted to talk about, because of course this all here assumes that we can linearly separate our data.
So where is so how do I want to share.
Yeah, okay, give me a second. Sorry, I have to make you co-host. Sorry.
Oh, okay.
Yes. Can you do it now? Please? Yes.
That's it. All right. So this thing here all assumes that we're able to find this hyperplane that linearly separates the points. So, but what do we do if we can't do that? So what I'm writing here is that the problem was again what I wrote here: minimize the norm of W such that this constraint here is satisfied for all the data points. But what if you can't necessarily separate them? Well, there are ways to get around this, and that's what we want to discuss now. So instead of having the conditions that why can't I write them? Well, my pen doesn't work anymore. That's the day. Anyway, we'll have to do without it. So if instead, so this is the condition we have when we can separate. So this is the one that characterizes the best hyperplane that separates them. But if we can relax this condition a little bit by saying, well, I don't necessarily need it to be bigger than or equal to 1. I just need it to be bigger than or equal to 1 minus some positive term. So some small positive term. So subtract something from the 1 here. It's easier to satisfy this condition here. So I'm introduce some new parameters, Ci bigger than or equal to 0, and I relax my condition to be that this dot product, this expression here, is bigger than or equal to not 1, but 1 minus Ci. So 1 minus Ci is a slightly smaller number, so it's a little bit easier to satisfy this inequality here. So if I put this in, well, I don't want the CIs to become arbitrarily large. So if I take very large CIs here, well, then this condition here just becomes empty, right? I can just take CI so big that this is almost minus infinity, and then this condition here is still always positive. So so it'll be vacuous. It'll be.
Do we want to force that epsilon I should be less than 1? Otherwise, the vector and the yi will be in opposite direction.
CI.
Yeah, Ci has to be less than 1.
No, we don't assume that. But if we make it bigger than 1, then this condition here is clearly satisfied. So we still want to limit CI somehow. We don't want to make it. We don't want to make the CIs too large so that they I mean, we still want some condition that the data points are further away from the line or from the hyperplane. So we don't want the CIs to become arbitrarily large. So instead of just minimize the norm of W, we make a regularization term here, which is we take the norm of W plus a constant C times the sum of these CIs here. You see, when we minimize this, right, then we also keep this term here not too large. So we can sort of play off the norm of W against the sum of these CIs here. So if we make C very, very large, take C very large, well, that means that in order to minimize, we have to make the CIs very, very small. And so that means that this condition here is almost satisfied. It's very close to being satisfied. The CIs have to be very small. If you, on the other hand, C is a small number, then the CIs can be larger and still have a minimum. So the new minimization problem is minimize this again subject to these conditions here. And that we can also, that's also a convex problem that can be again formulated in terms of alpha. So we can take the dual problem, which turns it into a problem of maximizing. So the minimization problem turns into a maximization problem. That becomes very simple. Becomes a problem of finding the alphas, again, the maximum. So I guess it should have been a plus. I wrote a minus on the board, so that was a mistake. So the sum of the alpha i's plus half of these things we have here, subject to, again, the sum of the yi times alpha I are 0. The alpha i's have to be positive. And again, W is then equal to yi alpha I xi. I also made a mistake when I wrote this. But now the condition is not just that alpha I is bigger than or equal to 0, but that alpha I is less than or equal to this constant C. So this problem here, minimizing this problem here, minimizing this expression here under these constraints becomes a problem of finding these alphas that maximizes this condition, satisfies this condition, and now satisfies not just that they're bigger than or equal to 0, but also that they're smaller than or equal to C. And so this problem, which seems to be somewhat more intractable, turns out to be, in the dual formulation here, turns out to be very, very simple. It just introduces this other constraint here that the alpha i's can't exceed C. And again, the W that we're looking for just becomes this linear combination of all the data vectors. And again, the alpha I is here only going to be non-zero when xi is a support vector. So that relaxes the requirement that we can separate them linearly, but it does not mean that we can solve any problem here. So if we look at a data set that looks like this here, so here we have two types. We have the crosses, say they're -1, have label -1, and the dots here outside have a label +1, but it's very clear that there's no possible way that we can linearly separate those in R2. There's no line that can separate all these points here. That's impossible. So and we could try to solve this by introducing these CIs. They're called slack variables because they sort of slack the problem a little bit. They make the problem a little less exact. They put a little slack in the problem. So there's no way we can do this, and we can separate these. But now the interesting idea is that suppose we map these points into R3, and we map them by this map here. It's a map from R2 into R3 that takes a point x1, x1, x2, and it sends it to the point x1, x2, and then the norm squared of this vector, or the distance from the origin. So what does that look like? Well, that sort of takes the plane in the R2 plane, and it folds it around this paraboloid here. And so this is a surface in R3 where you cut it. It's parabola. So this maps R2 into R3. And what happens to our data set here? Well, our data set here, we have these points here that are inside the circle here. The points that are inside the circle, right, they have distance from the origin less than the radius of the circle. Those that are outside, they have radius bigger, or they have distance bigger than the radius. So what happens is that those that are inside the circle, they will, their z coordinate, the coordinate this direction here, will be smaller than the radius of the circle. And those that lie outside the circle, they'll map to points whose z coordinate is bigger than the radius of the circle. And that means you can separate the data set now in R3 just by looking at the hyperplane that goes through that z equal to r. So there you'll have it. The points that were outside the circle, they will be above this, and the points that are below this were inside the circle will be below this hyperplane. So there you have a hyperplane that separates these two data sets. So the idea here is that by mapping the data set into a higher dimensional space, or in this case into R3, then you can solve the problem in the bigger space. And that turns out to be good enough. So in general, if we have a data set in Rn, say, so we have xi's, data vectors in Rn, and we have labels yi plus minus 1, then we can try to find a map into a bigger space such that in this bigger space, the transformed data set is separable, so that the points with the same labels, but where we map them into a bigger set, that they can be separated. So this turns out to be a really great idea, and that it works fantastically well.
So here, when you are mapping to the different space, the dimension of, we just need one more dimension, or the m has to be n.
No, you might need many more dimensions.
Okay, so it was just for the two-dimensional case.
Yeah, this was just for this example here, right? This is just for this example here. In general, you can need many more.
Okay.
But the thing that we'll get to, the thing that makes this, yeah, go ahead.
Do we have any kind of bound on what how much larger m must be, Niels?
No, it can be infinite dimensional, as a matter of fact.
But that means your data set is horrendously.
Yeah, that's what one would think, but as it turns out, it's not so bad. I'll show you why it's not so bad. It turns out that, yeah, even though if you map it into an infinite dimensional vector space, where you can't really do computations, it is not too difficult to, you can in fact still solve the problem. So the idea is that if we look at the maximization problem, the dual maximization problem, right? What we had over here was the, I wish my pen would work.
So it looks identical to the previous one, except there is a coordinate transformation in between.
Yeah, that's right. You have the phi xi dot phi xj, right?
Yeah.
You can see that.
Yeah.
But that's all we need. We only need the dot product. If we look at the conditions, we'll find W, right? W will be a vector in the bigger space, because there was a linear combination of the data points. So this now will be this linear combination of the transformed data points. So W will be a vector in the big space. But what is it we need in order to classify a new point? We're going to get a new point in Rn, and we want to classify that. So what we have to do is, well, we have to take and look at which side of the hyperplane it lies, right? And that means we have to dot it with, we have to map it into the big space, dotted with W at this this B here, this what we call it minus C prime before, and see if that's positive or negative. That'll determine the sign of the label. But again, let's look at what happens. How do we compute this? It's W dot phi of x, so that's a dot product in the big space. But if we look at what it is, it's yi alpha I phi xi, that's W. And then we dot this with phi of x. Again, what we find is that all we need to do is to know the dot product phi xi dot phi of x. So we don't actually need to know what these vectors themselves are. We just need to know what the dot product is. Same thing up here. All we need is the dot product. And this is a really great discovery that makes all this possible. There's a so-called kernel trick, because we only need to know the dot product. We don't need to know exactly what this phi is. And so the
and here we can make an ansatz for phi. We don't have to optimize on phi or anything, but as long as there's a hyperplane, we're done.
Yeah, well, yeah, that's fine. If we can find a hyperplane, we're done. That's fine. But we don't need to well,
the best phi or the best m or anything.
No, we don't care about the best phi. That doesn't matter. I mean, if you have any phi such that we can solve it up in Rm, then we're happy.
But I think we still need to find that Rm of phi where it's a hyperplane which is separating the data points.
Yeah, that's right.
That's the only condition.
But I think the comment I made, Manish, was that if you make a guess for phi and m, and as long as you luckily find a hyperplane that works, you're done.
Correct.
I don't need to find the best value of m or the best value of phi. I can just pick my favorite phi.
Yeah,
and
I think whatever separates will work, I guess.
Yeah. That's
But I'll say it's not so easy to guess a phi.
No, I know. I'm curious about all the quote-unquote goodness properties of these things, right?
Yeah,
what is a nice phi? What is a nice...
But as I said, the thing, it turns out you don't really need phi. What you do need is a way to take the dot product between two transformed vectors.
Yeah.
And if you think about that, what is that? Well, that's a function of two vectors in Rn. So you take two vectors in Rn, xi and xj, map them up by phi, and then take the dot product. So that's a function of two variables in Rn. So it takes two vectors in Rn and maps it to a real number. And so that's what we're going to look at. Instead of looking at phi, we're going to look at this map, which takes two vectors, map them up to Rm, and take the dot product up there. That's a function from Rn, cross Rn into R, which is given by this dot product here, right? So that's fine. But the thing that's interesting is that if we have such a function, k here, this function here satisfying certain conditions, then in fact there is a phi. We don't know. It's the proof is not something that constructs phi. That's. I mean, you can.
It's an existence result.
Yeah, it is. I mean, you can compute it, but it's a complete mess. It's not something you use for anything. But these functions, k here, they're known as kernel functions. And so, if you have such a kernel,
is there an intuitive way to see that computing or defining a kernel is easier than constructing the lifting coordinate transformation?
Yeah, absolutely. I can construct you 1,000 different kernels. It's very easy to construct kernels. It's very difficult to construct these feature functions, the phis, so the ones that map into R. They're very difficult to construct. But kernels are a dime a dozen. There are lots and lots of kernels. Because
they have this separable criteria. They seem to split into a product of two functions, right?
Well, I mean, that's the theorem is that you can split it into, if it satisfies these certain conditions, then you can split it into a product of these two of the feature function. Then it is of this form. That's a theorem. That's not an easy theorem to prove, but it can be shown. But there are lots of kernels, And let's see an example of such a thing. So a function, such a function, capital K, this is called a Mercer kernel. And the optimization problem now becomes maximizing this expression here. So now you can see that the dot product of phi of xi dot phi of xj has been replaced by the value of the kernel function. So if you have a kernel and you know how to compute this kernel, then you just plug that in instead of the dot products. And then you try to optimize this expression here. These are just certain numbers here. And you try to solve this this maximization problem. And then again, the function that you need in order to classify points, again, is just given by this expression here. You see now the dot product phi xi dot phi x is replaced by k xi comma x. So once you know the kernel function, you don't need to know phi. You can solve your problem. You can at least formulate the optimization problem, and you can also once you have solved this, you can classify new data points, and so the problem is solved in that case. So let's try let's try an example here of a. So I think Chidi has tried to solve this, right? Isn't that the one I put this on the homework, and there's no solution to it. So you're trying to find the either logistic regression or support vector, linear support vector machine that separates these points here. So this is known as this is the negative XOR. So if you have value, so you have a truth value. If they're different, you get it's false, and if they're equal, it's true. So this is a problem that is not linearly solvable, and you can't in fact, if you try to do either the try to do a support vector machine, a linear support vector machine, even with the slack variables, you can't solve it. You're not going to get a solution. So let's see that we can solve this by using a kernel. So well, if we try to solve the optimization problem without using a kernel, we only get the solution that all the alphas are 0, and that of course that's not a solution because it doesn't define a line. But let's try a kernel function now. Let's try a kernel function R2 cross R2 into R, which is very simple. It takes the dot product of the two vectors and squares it. So instead of just taking the dot product, which would be the original problem, we take the dot product and we square it. So this is in fact a kernel function. And in this case, one can in fact find the feature function. That's a function from R2 into R4, which is defined in this way here. It takes squares the first coordinate, and then second coordinate is the product of the two coordinates. The third one is also the product of the two coordinates. The fourth one is the square of the last coordinate. So that's a feature function from R2 into R4. And if you try to take 2 points and map them up to R4 and take their dot product up there, you'll find that dot product in R4 is precisely the square of that dot product in R2. So there we have an example of a kernel. The feature function is given here, and you can see the kernel function is very simple. It's just taking the dot product and squaring it. And let's try to see what happens if we now use this this kernel function here and try to look at our problem. So if we take these 4 points in R2 and transform them up to R4, we get these 4 points here. So these are 4 points in R4, And the constraint optimization problem is given by this. See here again, kxi comma xj is just the dot product squared. And if you write all this stuff out and tries to solve this subject to this condition here, alpha 0 minus alpha 1 plus alpha 2 minus alpha 3 is 0, and 0 less than or equal to alpha I less than or equal to c. C is some constant that we can choose. So if you try to solve this problem, it turns out that you can in fact solve it. So
sorry, Nils, I missed it. Like, how did we get like the those points in R4 as 0, 0, 0 and 1, 0, 0, and there was
you just map them by this function here, right? So let's see, we had the point, the 0 comma 0, right? So that obviously goes to 0 comma 0 comma 0 comma 0, right?
Okay.
And then we had the point 1 comma 0, that goes to 1.
Oh, okay, using this function.
0, 0, 0, and then, yeah, so it's just mapping the 4 points using this map here. So mapping it from R2 to R4. So, yeah, so we can go through the whole thing here and try to maximize this using this constraint here to express alpha 3 in terms of alpha 0, alpha 1, alpha 2, and then try to differentiate and blah, 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 and solving this. We get, in fact, a solution. And we get the solution. Alpha 0 is 4, alpha 1 is 2, alpha 2 is 4, and alpha 3 is 0. So if we take a constant big enough that we could take c equal to 5, we could take c equal to 7, or whatever, anything bigger than equal to 4 will work. Then we have the constraints satisfied, and so that means we get a solution. And so the W we get is a vector in R4, right? That's and if I write it out here, I get I have found my alphas. I have my 4 data points here. I can compute it, and I get that W is the vector 2, comma minus 2, comma minus 2, comma 2. So that's a vector in R4. And so I can dot that with vectors from R2. I can take a vector in R2, map it up to, we should also find B, as you said, we find, in fact, get B equal to minus 1. So if we go up to R4, then the hyperplane that separates these 4 points in R4 is given by this equation here, 2x1 minus 2x2 minus 2x3 plus 2x4 minus 1 equal to 0. So that's a hyperplane that separates these points in R4. But we can't draw that. We can't see what that is because we can't draw 4-dimensional pictures. So, but we can try to see what does it correspond to in R2. So we can take the map. We can take the points in R2 that map to this H. So that means we take all the points in R2 such that when we apply phi to it, we land in H. So that will be some configuration of points in R2. And you can, in fact, solve this again. You have points x1 comma x2 and R2 such that when you dot it with this vector W, you get 1. And if you write this out in terms of x1 and x2, you get 2x x1 and x2, you get 2x1 squared minus 4x1 x2 plus 2x2 squared equal to 1. So that's just, well, if you recognize this is divided through by 2, and you find that this is the configuration. There's a set of points x1 comma x2 and R2, which has the property that the difference, the square of the difference, is equal to a half. So this is pretty easy to see what that is, because you can just factor this out. So this means that x1 minus x2 is equal to plus minus 1 over the square root of 2. And so that gives you two lines. You get this line and this line. So the set that separates these points in R2 is not a line, it's two lines. And here it is. These are the two lines that separate these points in these 4 points in R2. You can see it separates the plus one label plus 1, that will be inside between these two lines, and the minus 1 will be outside. So we get not a line separating, we're getting and this is a quadratic. It doesn't look like quadratic, but it's two lines is quadratic. So it is a quadratic curve in R2 that separates these. So by using this kernel trick here, we were in fact equal to find a curve that separates these points, not linearly, but a quadratic curve that separates them. So this can be generalized. We can use all kinds of strange kernel functions. Here's one that is what is the Rbf function. This is a radial basis function. So this is a kernel function. This is say sigma squared times the exponential function of the square of the difference between the two vectors divided by some 2L squared. This is sigma squared is known as the variance. This is called the length scale, and L squared is a length scale. So this is the kernel function, but that corresponds to that in fact corresponds to a feature function that maps into an infinite dimensional vector space. So we don't want to deal with looking at vectors with infinitely many coordinates, but we don't have to, because all we need to do is to know what their dot product is in this infinite dimensional space, and the dot product of these two, of when you lift them or map them up to this big space, is just given by this function here. That's all we need, because that's all we need for the to solve the problem. And so that makes it possible to, if you remember some of the separators that we looked at in the beginning of this section here, where you're trying to let me go back and find it.
What is SVC? SVM was support vector machine. What is C stands for?
Classifier.
Classifier.
Support vector classifier. So we were looking at this data set here. And this is just clearly not linearly separable. And we tried different. Here's a linear SVM. This is in fact a support vector machine where we use this kernel, this Rbf Kernel, radial basis function kernel, and so that gives a somewhat better separation by if you adjust these hyperparameters, this length scale and the variance, you can get it to separate pretty well. So let's go over and look at some code and try this data set of this credit data. So let me go over to the I just need to start my Jupyter notebook. Okay, let me share the code again. Right. So here's the Jupyter notebook, and so again we have the imports NumPy, matplotlib, and I put in this command here, matplotlib inline with a percentage sign for to get my plots to be inside the notebook, so it doesn't create a external file. And here's the data set make moon, so that's what makes these things. So let me just let's just look at the same picture we got before. Yeah, so here's the data set, and we tried different things, logistic regression, to separate them. And here's the one that we use SVC. So by default, if you use SVC in sklearn, then it will by default use an Rbf kernel. So here we create an instance of the support vector machine, and we fit it to these data points here, and then we have this little graph program here that can sort of color the things, so we get a picture like this, which is what we had before. So let's go to this data set here. So we put it up. I put it up on the page, on the course page, so you have it. So we need to import pandas. So let's do that. And then we need to download the data sets. So if you download it from the page, you'll get some Excel file, and you can use pandas to load it into your program by using this pandas.read CSV. So it's actually an Excel file, but CSV is just as good. So we download it into the program, and let's just look at the beginning of the data set. So you can see here, what we have here is the data here for the loan data. Here we have the applicant's income, his age, the size of the loan, and then we have this loan to income, which is just the loan divided by the annual income. And then we have the outcome of what happened there within 10 years, whether the loan was defaulted or whether it was paid back. So 0 means it was paid back, and 1 means it's defaulted. And so we want to try to train an SVM, a support vector machine, to see if we can make a classifier that from these data, income, age, loan, and LTI, can determine or predict whether the applicant is going to default or whether we're going to get our money back. So we have this. There are 2,000 data points in this data set here. So we have the data vectors are 4-dimensional, right? They're 4 features, and we have labels here. Labels should be, and when we use support vector machines, should be -1 and 1. So here's the zeros and 1. So we have to do a little bit of engineering here to change the zeros to -1s. So let's try to split this data set into a training set and a test set. So we're gonna train on the training set, and then we're gonna test it out on the test set. So let's import the train test split that we have talked about before. That's the one that automatically creates a training set and a test set. So let's import that. And then I want to separate the labels and the data set. So I do that here by here. I only want to take I want to leave out the client ID because that's not going to have any effect. So that's column number 0. So for the data vectors, I'm going to take the columns 1, 2, 3, and 4. So I'm going to select columns between 1 and not including 5. So that's simply using this command here, and the labels are, well, they're in column 5, so in the last one. So that's what I do here. So then applying this train test split, I can split it into a training set and a test set. So I choose 25% to go in my test set, and I shuffle it so it gets mixed up here. It doesn't just take it in the order it has here. So it's randomized pretty well. Then I do a little bit of fiddling around here with getting the zeros turn into -1s, and so there are definitely more elegant ways of doing that. But I just make it -1 if y is 0, and I put it equal to 1 if it's not equal. So if it's already 1. So I just make these train and test sets now, and they are now, instead of being 1s and 0s, they are 1s and -1. So let's just look at one of them so we can. Oops. I better do it first. Instead of just talking, I just talk about it. The computer doesn't understand that I wanted to actually run the code, but if we do it now, it should be better. So you can see now that the labels are -1s and 1s, so they're mostly -1s, and -1 means no default. 1 is a default. So then we also looked at, as we said, that if you look at the magnitude of these numbers here, they're very different. So the LTI is a number smaller than 1. The income is in the tens of thousands. The age is in the teens, so between 0 and 100, and the loan are in the thousands. So they're very different magnitudes, and so we want to scale them so that they sort of have the same magnitude. And so there are different ways of doing that. So in sklearn, we have a number of different scales. I'm choosing the standard scaler here. The standard scaler here, all it does is it turns them into mean 0 and the standard deviation 1. So it subtracts the mean and it divides it by the standard deviation. And so this standard scaler here is another class. So I instantiate it, here, and then I can both fit it and transform x, because it has to figure out what is the mean and what is the standard deviation. So it has to do that by looking at the training data. So it takes the training data, computes the mean and the standard deviation, then performs the transform. So it fits and transforms in one. So fit underscore transform, that does the both the computing the norm, computing the mean and the standard deviation, and also does the scaling. And then, as we also discussed, it's very important that you use the same mean and standard deviation when you want to scale the test set, because the test set, you can't compute the mean and the standard deviation. That would be cheating if you did that, because you can't touch the test set. So you have to use the same mean and standard deviation that you found in the I lost power on the video. Hold on just a second. Yep. So we're gonna use the same numbers there to scale the test set, and that is a great thing about the using this standard scaler, using the fact here that it's an object of this class here, because now when we fit transform on X train, then we store the mean and the standard deviation. So we just apply that to, you see here, when we do X test, we only do the transform. We don't do the fit. So let's try to apply a couple of support vector machines and see how well they perform. So first we take a linear kernel. So linear kernel, that means that we don't do any feature transformations. The feature map is the identity. And so the kernel function is just the function that takes a dot product. It takes k of x comma y is just a dot product, x times x dot y. So that gives us the linear kernel. That means there's no feature transformation. So let's see how well that performs.
And Niels, this C is the what you call it, regularization term?
Yeah. There was the C was that that term that we multiplied these.
W1 by lambda.
Yeah. So again, we instantiated with a linear kernel, and C equal to 20, and then we fit it on the train set with the training vectors, the 4-dimensional training vectors, and then the labels. And let's see how well it does on the test set. So that means we're going to use the predict function on the test set to find out what labels it predicts for the data we held out. So again, we have scaled the test set using the same parameters as we computed from the train set, and we take the predicted values, and then we can look at the see how well it did by running the accuracy score. The accuracy score takes the actual labels and it compares it to the predicted labels. So it's a very simple function. And we have forgotten to import the accuracy score. So that code should be somewhere up here. It is. So I better import that too. So let's see. So we get a test score of 96%. So that's pretty good. The confusion matrix. We can also see the confusion matrix here is how many. So this is -1. So that's no default. How many of these does it predict correctly? So as we can see here, there are 434 that don't default, and of those 434, it correctly predicts the 424, and 10 it mispredicts. Here are the defaults, and of the defaults, so there are 66 defaults in the test set, and of those it correctly predicts the 56 and incorrectly predicts the 10. So that's what the confusion matrix does. So if you want to, we can see how many there are of each here by using this counter here. So you can see that there, as I said, 434 non-defaults and 66 defaults. So we can also see how well it performs on the training sets, and it actually does worse than that's strange. Let's try a logistic regression and see how well that does. Again, I forgot to import it. This is not so good. That's up here. So let's see what we get if we use logistic regression. So I should say that the thing we did up here, that was using a linear kernel. So we're separating by a linear subspace, and we can fit. So here I do. This is obviously also a linear subspace that separates here using logistic regression. And let's see what we get here. We get actually slightly better, 96.6%. So let's finally try it with the Rbf kernel. So again, the Rbf kernel is the default for SVCs. I don't have to put any kernel in here. And again, I take it now. I took C to equal to be 1,000. So I have very little constraint on my C on the slack variables. So let's see what we get here. We fit. We predict. And let's see what we get. Accuracy score. So we get a substantially better result. We get 99% correct precision on the test set. So using the Rbf kernel here gives us a better result there. We could try other things if we want. We can try other kernels. By putting the keyword kernel into polynomial, if I'm not mistaken, degree equal to 2. So we could take a quadratic kernel like we did before and see what we get here. So let's
You don't have to give C here, no?
I can if I don't put any C in, it defaults to. I can yes, I should put a C in and put a 100 in. If I don't put a C in, it defaults to 1.
Okay.
So let's see how well that performed. So let's look at predictions. Yeah, so writing code live is not recommended. It's very easy to make mistakes.
You have to keep up the entertaining dialogue while you type, Neil.
Yeah, right. I know. It's scary. Okay, so let's see. We got. Let's see what we get for the. So we got a pretty lousy 90%, right? So even the it might be that we can mess around with the C here, maybe. So the bigger you make C, right, the less restrictive it is, because you had this the alphas have to be between 0 and C. So the bigger C you take, the less restrictions you have on. So that improved it a little bit. So take a bigger C, so it puts fewer restrictions on the alphas. I get a better score. Let me try to get it all the way up to 10,000. It gets a little bit better. But the best of the ones we showed, which we tried here, was definitely the Rbf that had a test score of 99%. So that's a pretty good performance, right? It will correctly predict in 99% of the cases. So that.
So, Professor,
Yeah.
if we change if you reduce the restriction for the SVC with the Rbf kernel, I don't think it's going to make much more difference, right? Because it's already.
No, probably not. I mean, we can try it. We can try to go up to 10,000 and see what we got. No, it probably doesn't make a big difference. We can try. If we lower it, yeah, it probably will make some difference. No, actually, but it made it better. So I don't know. That's kind of strange. Let's try to make it much smaller. No, that may. So it's again it's a matter of if you restrict, right, then again you have you prevent overfitting a little bit. So if you make it make C very small, then you restrict your alphas, and that will tend to you restrict your or to alleviate overfitting. So if you take well, that's not good either. Yeah, so it looks like t equal to 1. Again, you should of course do a grid search here to find the best. Now, what we're doing here is absolutely, of course, is illegal because we're trying to optimize C on the test set, which is something we must not do. So it's completely illegal what we're doing here. But
you converted your test set into your training set.
yeah, well, that's yeah, right. But I should not. I should have a validation set and try to optimize on that and then look and see. But as you can see here, the support vector machine with Rbf kernel performs pretty well on this data set, and it's a very good classifier.
So one question here. Go ahead.
Yeah.
Sorry, Niels, is that a statement about this data set, or is that a statement about the radial basis function generally doing better?
Well, I mean, it will certainly fit the training set better because I mean here in sklearn it optimizes the variance and the length scale automatically. This sigma squared and this L squared. So it also finds the best ones for those. It is a very flexible. It's a very flexible kernel that allows you to. It basically allows you to separate any training set, but that we know does not necessarily mean that that is going to predict well. But what you get here is when you use the Rbf kernels is that the separating the decision boundary is going to be a smooth curve.
Yeah.
So that's that is a good thing. I mean, you're not going to get some very strange curve that has kinks and what have you that just tries to fit the training set. But the Rbf guarantees that the separating the decision boundary is always a smooth. In this case, it's not a curve, but a smooth manifold, as it's called. So that tends to make sure that it doesn't overfit too badly, and so that's why I think the kernel, the Rbf kernel, is pretty good. There are a number of other kernels that also do a very good job, and there are some very complicated ones. But you can literally make thousands and thousands of kernels. It's very easy to make kernels. If you have kernels, if you take two kernels and add them, you get a new kernel. If you take two kernels and multiply them as functions, you get a new kernel. So you can really make lots and lots of kernels. So it's very easy to make all kinds of kernels, and there are general ways of making kernels that can, and so it's in some specialized data sets you might be better served by taking some pretty exotic kernel and try to do that. But I can't give a real sort of rule of thumb for how to do it. The Rbf kernel works pretty well in most cases, but there could be some exotic cases where it wouldn't work so well. But the main thing about the Rbf kernel is that the decision boundary is a smooth thing. Yeah.
Yeah, I think it's a pretty cool idea of mapping from n-dimensional plane to a high-dimensional plane for separating.
Yeah, it is.
Came up with a very cool idea.
Yeah, it's a very cool. It's actually a beautiful idea. It's very ingenious. So it was yeah. It's beautiful, beautiful math.
So Niels, what is the algebraic geometry in UC that we can't see?
Well, I mean, I can't see into 4 dimensions, but I think it's a I mean, I enjoy the what can I say, the cleverness in the idea here, right? The fact that you see that the problem, the optimization problem you get, only depends on the dot products between the vectors and not on the vectors themselves. And that's a really interesting observation. I mean, this is done by a Russian named Vapnik. He was working at.
Is he the professor at Columbia University?
No, he was. I think he was working at IBM, if I'm not mistaken. I mean, this was done in the 70s, I think, 60s or 70s. It's not that old.
Yeah, I know. There's a guy who did who came up with SVM. He came for presentation at our firm, and
did he? Okay.
He's a Russian guy. He has a book on SVM as well, and he's a part-time professor at Columbia as well. So I think
okay, but yeah, I wouldn't be surprised. But he must be pretty old now.
Yeah, he was pretty old.
Yeah. Okay. Yeah. Yeah. It's a very nice idea. The only problem is that it doesn't scale so well. So if you have these enormous data sets, you're not gonna be able to use it because it's simply too slow. I mean, some of the algorithms to perform the optimization, I mean, there are quadratic optimizers, so there are software packages that does it, but they really don't work well when the data set becomes big. They can't do it. And but there are other sort of approximate that constructs sequences. There's something called the SMO, sequential minimal optimization, which is a pretty clever idea in the sense that it says, well, we can't optimize one alpha at a time, because if we change one alpha, then we're going to minimize we're going to ruin the constraint. So this constraint that the sum of the yi's times the alpha i's are equal to 0. So if we just change one of the alpha i's, then we're gonna violate that constraint. So we can't do that. But the idea is that we're gonna change 2 of them at a time. So if we take 2 of them and we keep their sort of the relation. So they take y1 and y2, or alpha 1 and alpha 2, and we keep the condition that y1 alpha 1 plus y2 alpha 2 is equal to some fixed thing. We don't change that particular number. We can change them amongst each other so that their relation is still satisfied. And you can use that to optimize to solve this optimization problem. And there are a number of what can I say, some more, some less clever ideas of how to select the pairs of alphas that you're going to optimize, and that if you just try to do the randomly, you can do that. You can randomly select pairs, but that is not the best way of doing it. There are other ways that are much better and makes it converge much faster. So.
But Niels, there's also, I guess, intuitively, I feel that it's unclear that having large amount, if you're really trying to isolate a hyperplane,
yeah,
it's not like you're better characterizing the hyperplane by adding a lot of extra points.
No, but you don't want to. I mean, it's not necessarily adding them. I mean, it's. I mean, if you,
no, I'm just making a silly example where, let's say, the dividing boundary is the y-axis.
Yeah.
And if I add 1 billion points into this problem, it makes the optimization slower.
Yeah, but I mean, again, but if you start out with a a data set, you really, and if it's a high dimensional data set, you really have very little idea of what it looks like. You can certainly try to do things like projecting it down to lower the dimension.
I'm talking about not the number of features, but the number of points, number of sample data points.
Yeah, but again, you need to sort of, if you want to do that, then you need to have some idea of where your separator is to know which ones you can throw out. If you don't,
But I was saying, suppose let's say you have 10,000 points and you randomly picked 5,000. I'm just making a scenario.
Uh-huh.
And you resample the 5,000 again, and you find that your hypersurface is fairly stable. Or you did 5,000.
Yeah, sure. You could do it like subsampling. Yeah, you could. Yeah. You could try to do that. That's yeah.
So then you could argue for certain data sets that just because I have 10 billion points, I'm not really making the hypersurface any better by throwing a lot of points and slowing down.
But that'll depend on the data set, right?
Yeah.
So in some data sets that could possibly be true.
Yeah.
By subsampling, you could get pretty good results.
Yes.
That's possible.
There's one technical question. Is there an easy way to see which kind of kernels will produce smooth hyperplanes in the projection? Is there a criteria on the kernel?
Is there what?
Is there a criteria on the kernel that will say that this type of kernels are likely to produce smooth?
Right, there is. I mean, if you take a polynomial kernel of degree n, then it'll be smooth up to degree n. I think, if I'm not mistaken. So that will give you decision boundaries that are smooth up to degree n. So it has continuous partial derivatives up to degree n. And the Rbf, you can sort of view that as a infinite polynomial infinite degree. So that'll be called C infinity. That'll have derivatives of all degrees.
Any C infinity function could work, but does it? So what? I'm trying to understand what are the criteria. Like that also looks like a function with compact support of some kind, right? Because it's exponentially damped.
It does not have. I mean, it's non-zero everywhere, but of course it's depending on the length scale there. It drops off very quickly.
Yeah.
So it will tend to so if you start with one point and look at what it looks as a function of another point, it will drop off pretty quickly as you take points further away from the fixed points. So depending on the length scale. But yeah, I mean it's
that is a beautiful function. The radio.
Yeah, it is. Rbf. Yeah, it is. I mean it's like a Gaussian, right?
Yeah.
But you can try other. I mean you can certainly try many other things. So.
And there's one unrelated questions. He talked about least angle regression, LARS, right? Do we have that as a standard method in scikit-learn or no?
What was it called?
It's called LARS, least angle regression, where you regress against the first variable which has a maximum correlation with the y, and take some multiple times that first variable, so that now the correlation between the first variable and the residual of the first variable and second variable.
I don't know. I haven't seen it. There's probably some package that can do, but I haven't seen it. Okay. I'm not a big fan of such methods, to be honest. So it's for economists to use that kind of method. So,
Yeah, Professor, in the example with that 4 data points that you used to explain,
right.
when we flip the labels for the top 2 points, right?
Yeah.
Still, we were not able to converge to a solution, right? Why would that be? I thought.
No, if you flip, then it should be.
No, then it became singular. Last time when we were doing
Yeah, it became singular. Yeah.
when the data points were flipped, it was coming after few iterations. It was not converging. We did that using the logistic regression.
Yeah.
Yeah, I mean,
Yeah.
I mean, they would become singular because there would be if you don't regularize it, right?
Correct.
So if I flip the 2 points here, right, the labels here, right, then it obviously becomes separable.
Yeah.
Right, but then if it's completely separable, then logistic regression will not converge. So there you need to regularize. But if you regularize, you'll get a solution, right?
Yeah, I thought, Manish, we were running the regularized Hessian.
Yeah, I think we have to look at it. We were running regularized one because it was the Hessian was regularized Hessian, right? And the gradient was also regularized. So it was still getting into singular case.
Right. I mean, when you
I'll send you that note. It's the one. It's your notebook from previous one.
Yeah. So you did that not work? Did you not get a solution? And,
you used the Newton descent method where it was like the gradient times like Hessian inverse.
Right.
And then that part, I think that the code for Hessian was getting singular, right, Tejas? I think so.
Yeah.
Yeah.
Oh, yeah. Well, that's very possible. Yeah, I mean, the thing is that the loss function you get there is, I mean, I think I showed a picture of the loss function, right? It becomes very close to being linear as you go further away from the minimum. And so if you're far away from the minimum, the loss function is, as you get further away from the minimum, the loss function is almost linear. And that means that the Hessian is going to be 0. Right, the double derivative of a linear function is 0. So that's something you definitely have to watch out for. If you're very far away from the minimum of the loss function, then Newton's method will probably fail because of the. You can try to use which is the BFGS. Minimizer. That should work in the sense that it's similar to the Newton's method. It converges very fast, but it does not try to compute the Hessian. It approximates the Hessian, and as you go further along in your sequence, it gets closer and closer to the Hessian. But it's also a very clever observation. And the observation is you don't really need to compute the Hessian because all you need to know is the value of the Hessian, of the inverse Hessian on one vector, namely the gradient. Right? You don't need to know the whole Hessian. You just need to compute it on one vector. And that can be used to construct an algorithm that is almost as fast as Newton's, but doesn't fall into those problems. So this is the BFGS, I think it's called, Broyden, Goldfarb, whatever. So that's basically the standard algorithm that everybody uses. So that's also an SK-learn.
Thanks a lot, Niels.
All right. Okay.
I
Thank you
think
so much, Niels.
try these methods.
What's that?
I'll try to find some data sets where I'll see.
Yeah. Oh, for sure. Yeah.
I'll let you know next week how it does.
It sounds great.
Yeah.
I look forward to it. Okay.
Okay.
Thank you so much.
Thank you so much.
Okay. Sure. Take care. Bye bye.
Bye.